So the output will be the model will be operate as a AND gate or AND operations. Okay, and then if you apply 0 and 1, okay, apply 0 and 1 or 1 and 0 or 1 1 0 0. Okay, the output, this output will be just approximately 0 or 1. Okay, it will be like the AND gate. It just means if 0 0, okay, you can calculate send ASML. If 0 0, okay, so this 2 will be 0, so minus 30, and then minus 30 is mean approximately equal to here, okay, approximately equal to 0, so it's just 0. And then if we consider 0 1, okay, so that is mean minus 10. Minus 10 is mean also about here, so it is mean 0, so this is 0. And 1 0 is also minus 10 0. And then if we consider 1 1, okay, 1 1 is will be equal to 10. G10 is this mean round about here, so it's approximately equal to 1. Okay, so that's why this model, okay, will be operate as a AND gate. And then similarly, we can construct for the OR gate by using one neutron or NOT gate or any other gate. Okay, this is mean NOT gate. Okay, we can construct by using the neutron. But how about the XOR? Exclusive OR. Okay, this one. Okay, for each of this one, okay, it can construct it easily because we can draw the linear line. Okay, let me draw them here. Okay, for AND gate, let me draw in here. We can divide it into 4 regions. Okay, so this is output 0 0 0 1. Okay, if we divide it like this, sorry, 1 is here. Okay, so this is X and Y. Okay, we can divide like this. Okay, and for this one also, we have 1 1 1 0. Okay, we can divide like this. Sorry, here. We can divide like this. For this one also, we can divide like this. Okay, of course not. Okay. This is me actually 1. Okay, and then also this one, we can divide by using just one line. Okay, but for the XOR, we cannot divide by using not only one line. Okay, so if we divide like this, okay, actually this is 0 0, this is 1 1. Okay, if you still remember about the XOR, okay, X and Y, 0 0, the output will be 0 0 1, output will be 1 1 0, output will be 1 1 1, output will be 0. Okay, in this case, one neutron is not enough anymore. Okay, so in that case, we have to consider neural network. Okay, and then for this XOR operation, okay, for this XOR operation, okay, we can combine, okay, we can combine this AND gate, okay, and this NOT gate, okay, and this OR gate. And then if we combine them together, okay, we can get the XOR, okay, because for the XOR, you can consider by using in the logic calculation, okay. So anyway, for the XOR, okay, we cannot divide it then by using not only one line, okay. In that case, if you apply the neural network like this, okay, we can separate them easily, okay. And then if you apply this one, if we supply 0 1, okay, of course you will get 1 in here, okay, 1 0, you will get 1 in here. You can try by yourself, okay. So that's why the neural network is very useful. Okay, and then if it can learn, okay, well, it can predict or it can classify, okay, many things. Okay, so it can classify or it can make the decision well. It's depend on the learning, okay, because this is part of the machine learning. Okay, the neural network have to learn fast. Okay, so the learning is mean in the technically we call it a training. Okay, how we can train the network or how we can train the model. Okay, so how can we train the model? Okay, actually, if we look at in the neural network or just one neutron, okay, that decision, okay, is mainly based on this weight and this bias. Okay, you have to find accurate or suitable value of the weight, okay, to make the good or bad decision of the model. Okay, so to find that suitable value of the weight, we call it a learning or training. Okay, so for one perceptron, okay, we use a lot of term. Okay, perceptron is mean actually is one neutron or just one unit. Okay, it's this one. Okay, for this one, okay, and then we assume that sorry. Okay, we we try to predict something, okay, that is mean HAs, okay, and then we have the Y. Y is mean, let's say this is the desire, okay. Let me define it like this here. Okay, this is mean our predict value or output of the model. Okay, and then Y in here is our desired output. Okay, to train or to let's learn the model. Okay, we should have this desired output. Okay, and that is respected input set. Okay, H1, H2, H3. And then less than this is pass through the model and then calculate the predict output. Okay, based on the first initial weight. Okay, after that, we have to update or we have to modify the weight. Okay, based on the how far or how different between our desired output and the predict output. Okay, so that is mean we call it a error. Okay, so error in this case is, okay, y is mean our desired output, and this is the output of our model. Okay, we calculate this error. Okay, and then this perceptron learning rule is a very simple one. Okay, how we do is we find the error. Okay, and then we multiply with that input A. Okay, and then also, okay, in here, this is mean actually the error. Okay, but actually it's based on the real calculations. Okay, and then error. Okay, and this one is multiplied with our input pattern. Okay, and also multiply with the alpha. Okay, we will discuss more detail about that alpha in the later. That is because a learning rate. Okay, if F4 is too large, you can find the final weight in the short die. If too low, okay, it will take die. Okay, that is the landing rate. And this formula, okay, so actually this one, okay, this is the weight. Okay, this is mean the current weight. Okay, this W. Added with this one, you will get the new weight. Okay, so this one we call it a Perceptron landing rule. Okay, so this one is the basis one. Okay, it's proposed by this 2% in the 1969. Okay, but nowadays we have variation of this rule applied in the real neural network. Okay, but this one is just a basis one. Okay, this rule is very simple. Okay, what is that? It just means if your prediction is correct, okay, it just means these two are the same, you will get the 0. So the current weight will be the same as the new weight. So it doesn't change to the weight. Okay, and then if the output is low, okay, for example, for the binary case, this is mean the prediction output is 0, and then the desired output is 1. Okay, so it just mean 1 minus 0. It just mean this weight, okay, the new weight will be equal to old weight plus alpha s. Okay, so that is mean it's increased. Okay, the weight for all input with R 1. Okay, because this one is we just consider the binary. Okay, so let's say 1. Okay, and then if height, okay, height it means our desired value is small, the output of the desired value is small, the output of the model is height. Okay, for example, 0 and 1. It will be equal to minus 1. Okay, in that case, the new weight will be equal to old weight, okay, minus alpha s. So it just means if your error, if your output is, okay, too high, okay, so it will be reduce the weight, okay, decrease the weight for all input. Okay, and if your output is small, okay, it will try to increase the weight. Okay, so this rule we call it a perceptron learning rule. Okay, so if the set of the weight that are consistent with the training data, okay, that data is linearly separatable, the perceptron learning will be converged. Okay, it will find the optimized. Okay, but this one can apply only for this one linearly separatable model. Okay, but in the new real neural network, okay, we have to apply the we have to apply the other verification, modification based on this rule, okay, especially for this error 10. Okay, so in this case, let's try send example. Okay, let's say so let me skip this one, okay? But we have many slides here. Okay, so that's why in the learning of the real neural network, okay, is use another method, okay, and that calculation we call it a backpropagation, okay. Sorry, I think this one is to draw. And then previously, I just show you the feed forward, okay? Forward propagation, okay? And to do the learning or to update the weight or the weight, okay, or including bias, okay, that process we call it a back propagation, okay. Similar to the Perceptron learning algorithm, here like this, okay, we cycle our assemble, okay. That is mean if the output of the network is correct, there's no changes, okay. But in the real case, okay, it will not correct exactly, okay. And if there's an error, okay, the weight will be adjusted to reduce the error, okay. But this no changes is mean in the real case will not happen, okay. But that changes is getting smaller and smaller, okay. It just mean the error is getting smaller and smaller, okay. We have to stop. So that is mean we have to use a optimization method, okay. And for the optimization method, I will discuss more detail in the next week, okay. Today I will just show you some example, okay. But in the neural network, okay, we have many neurons here, okay. So this output is okay. This output y is not only depend on this neutron, it's also depend on this one, this one, this one, this one, this one. This mean it's also depend on this weight, this weight, this weight. Okay. So how they do is if there's an error in the y, okay, how they do is they blame, okay, all the node, all the unit, okay, and that blame is not only to the one, it will be divided to the contribute weight, okay, because this output is the contribution of all the nodes, okay, this error should be responsible of all the nodes. So that's why they have to, the error should be divided and then taken care by each weight, okay, that apply in the neural network. Okay, so in the neural network, instead of just calculating the error, okay, y minus 8 is, okay, in many optimization methods, we have to use a cost function. Okay, the cost function is meant to calculate the error. Okay, but that is not the simple one as this one. Okay, it will be like that. Function of, okay, that error difference. Okay, and one of the cost function for the logistic regression, okay, is in here. Let me use like the J. Okay, this is mean the cost function. Normally the cost function, okay, in the optimization, okay, we use as a cost function because we want to find the minimum cost, okay, or another term is minimum error, okay. So that's why it's called as a cost function or error function, okay. And then in this case, that one, okay, we define with the weight W, okay, because we want to find the value of the weight, okay, with the minimum error or minimum cost. That's why this one with the define with the function of W, weight, okay. This weight is all weight, okay. And for the one logistic regressions, okay, it will be equal to 1 by n summation of I is equal to 1 to n, okay. So the n is mean the number of input yi, sorry, number of output, okay, yi log h w is I plus 1 minus y I log okay. So actually in here we have also the regulation term, but for today let me skip that one, okay. I will not consider. So normally for the logistic regression, okay, for the cost function we use this one, okay. Or for the neural network, okay, for the NN we have to consider many, okay, many of this one. So that's why you may have the summation term in here, okay. The first one is a number of node, okay, this is the number of node, okay, and for number of layer, okay, and the rest is the same as in here, okay, because this is just for the one neutron, okay. In the neural network you have many neutron or many units, you have to calculate like this, okay. But this one I will discuss more detail in the next week, okay. And then optimization is this mean for this one, okay, we need to find minimum, okay, of in terms of the weight W, okay, like this. So in this case, actually what we have to do is we have to calculate this one, that JW, okay, and also we have to calculate the partial derivative of that W, J, W, okay, like this. So to calculate that weight or to do the training, as I mentioned that, okay, what do we need? We need a training data set, okay, or we call it a training instance. Not only one is enough, actually we have the data set, okay. Each of them have the input and its output like this, okay. If we have that one, okay, we can calculate the W, okay, in this case W and B. And then if we can design well, okay, we can calculate the optimize W and B, okay, and then our model will be perform well, okay. So what we have to do after we got this X and Y set, data set, okay, we have to calculate the forward propagation first, okay. So in this model, okay, so in this one, we have the how many layer? 4 layer, okay. So this 2 is a hidden layer, okay. This is the output layer, okay. This is the input layer, okay. So this is mean we have W1 in here, okay. We have W2 in here, and we have W3 in here. Okay, so in the landing, what we have to do is we have to calculate all for the W. Okay, first, initially we can assign that W with the random number. Okay, and then based on that one, we have this input A's. Okay, this is 8, and this is Y. Okay, based on this X and Y. Sorry, yes. Okay, with this X, by using this initialized W, we can calculate the estimate or predicted Y. Okay, so let me define that 2Y clearly in here. Okay, this one is being the output of the model. Okay, that we call as a predict. Okay, and then this Y from the data set is our desire or our target output. Okay, and then if we have this data set, okay, first we have to calculate this Y hat. Okay, so for that one, this is a factor, this is a factor. Okay, for that one, we can calculate one by one. First, we can calculate the A1 factor. It can be just a ace because this one is just an input layer. Okay, and then after that, we can calculate the C2. Okay, C2 is before the activation function in here. Okay, it will be equal to W1 A1 plus B1. Okay, and then after that, we can calculate this A2. This is passed through the activation functions C2 like this. And then also we can calculate for the three. Okay, so that is mean W2 multiplied with A2 plus B2. Okay, so actually this W are just a initial number. Okay, and after that we can calculate the A3. Okay, so this is mean A3, and then finally we can calculate the output. Okay, C4, this is mean W3 multiplied with, okay, order factor. Okay, 3 multiplied with A3 plus B3 factor. And then from here we can calculate the A4 is equal to G C3, sorry, 4. Like this. Okay, so however, the network is large. Okay, by using this metric calculations, okay, you can calculate the forward propagation easily. Okay, and then this one we call it a H W based on the current weight input of ACE, or we call it a ACE get. Okay, after we got this output, okay, we can find the error, or we can calculate the cost function. Okay, to do the network propagation. Okay, so as I mentioned in the previous slides, okay, for each hidden node J, is responsible for some fraction of the error. Okay, so in this case, the error. Okay, so error is mean this signal. Okay, so this error is responsible for all the node in the hidden layer. Okay, as well as in the output because it's mean the weight. Okay, for the same fraction of the error. Okay, for the layer in each of the output node J to which is connected. Okay, and that's why for each layer, okay, for that error is divided according to the strength of the connected between hidden node and the output. Okay, so that is mean depend on the previous weight. Okay, so then the blame is propagated back to the error value for the all hidden layer one by one. Okay, that we call as a backward propagation. Okay, so the idea is like this. Okay, so actually this is for the B, this is for the B. Okay, but to be the easy, okay, in this case we put it that B as a weight omega 0. Okay, omega 0 1, omega 0 2, like this. Okay, and this one is okay, like this, and this one is W 1 1, W 1. Sorry, this is 1 0 2 0. Okay, this is 1 1, this is 2 1, 4 1 1 1 1. Okay, and then this is mean W2, sorry, 1 2, then this W2 2, like this. Okay, and that's why instead of writing B, okay, we combine them together as a W, okay, like this. And then in this case, okay, after we got all the initial W, and then after we got the A's, we can calculate the Y hat or H W A's, like this. Okay, and then we also know that our desired Y, okay, and then we can calculate this error. Okay, based on the function of okay, this is the error. Okay, this is actually the partial derivative of okay, the error 1, error J for each layer. This is mean the error function, okay, or cost function. Or maybe I can say that it is like that. Maybe we can say that the changes in error. Okay, and that error changes where we distributed all of the node in here. Okay, so that's why in here this one delta JL is we call it a error of the node J as a layer L. Okay, actually it's calculated. Okay, after we define the cost function based on the previous slides. Okay, what we have to do is we have to actually this one is data is mean the changes in the error. Okay, based on this weight. Okay, so that is mean we have to find derivative of this one. Okay, so that is mean this error is mean partial derivative of. Okay, so this is actually not W. This is for S, or maybe this is a input. For each layer, okay, we have to consider like this is a partial derivative of the input for that layer of the call function, like this. Okay, in this case, the call function is this one, okay, for the logistic regression, okay, or maybe you can apply other cost function also. Okay, so based on that one, for example, we have output, okay, like this, and then this is our output layer or output node, okay, and for that output node, okay, this C1 4 is mean actually the calculation of, okay, multiplication of W 4 with this A1, A2 of 3, A3. Okay, so this one is for this one, okay, and then this one is G of C1 4, like this. So if we got this one, okay, so this is mean this one. Okay, this is mean this one, and this is mean our desired output. Okay. Okay, so let's assume that this is just an error. Okay, the error between the output and input. Okay, and then that is mean the sigma 4. Okay, but please keep in mind that that signal is actually, you have to calculate it from this formula. Okay. Okay, and in this case, let's consider just a different the error. Okay, so this error is the error happened in here. Okay, and then that error is due to this node as well as this two node. Okay, pass through this weight. So they will have the contribution of that error. Okay, so that error we can that what to here and here. Okay, to transfer back that error to here. Okay, so for that error we call it a sigma 2 layer 3 for the node 2 layer 3. Okay, this will be equal to W. Okay, in this case W 1 2 3. Okay, because for this error, okay, this error is not only from this one. It's depend on the how much contribution is depend on this weight. Okay, so that's why we have to multiply with the weight. Okay, to get this error. Okay, so this error multiplying with this weight, so we will get this error. And similarly, we can calculate the error in error contribution in this node. Okay, so this is mean this is W 1 2 3. Okay, and for this one, we have the weight W113. Okay, to got this error, okay, we have to multiply the weight, the error in the last node, output node, multiply with this weight. Okay, like this. And also for this sigma 1, sigma 1 2, okay, this is mean for this one. Okay, we have to consider the error. Okay, but for this node, it's connected to this one and this one, two nodes. Okay, so that's why it have the responsibility to the error for this node and error for this nodes. Okay, so that's why to calculate this sigma 1 layer 2, we have to consider this weight. Okay, this is from the layer 2, right? And this is for 1 1, and this is for 2 1 layer 2. Okay, so to calculate this one, okay, this is the error from here. Okay, multiply with W112 with the error of sigma 1 3 plus also this error is this contribution of this amount with this error like this. Okay, and similarly for the sigma 2 2, we can calculate like this. One, two, two. So that is mean this weight multiplied with this error, sigma 1, 3, plus multiply with this weight. This is mean W 2, 2 from the layer 2, sigma 2, 3, like this. Okay. Let me write down. This is W, this is mean W. Okay, W1, 2, 2, and W2, 2, 2, like this. Okay, so that is mean in the back propagation. Okay, we distribute the error according to the weight like this. Okay, and then based on the error, okay, based on that error, okay, we have to update. Okay, we have to update the weight accordingly. Okay, so in that propagations, okay, I could not finish this slides. So for this model, okay, so what we have to do first is we have to calculate this error for each layer. Okay, for the first one is, for the simple case, we just calculate the error between output of the model and desired output. Okay, and then we propagate then, okay, back to the next layer. Okay, so that is mean this one is multiplied with method of W, sorry, not 4, W3. Okay, so this is W3, this is W2, and this is W1. Okay, and for the 2, two, 3, yes, like this. Okay, and then for this part, I will discuss more detail in the next week. Okay, and then this is how we do the backward propagations. Okay. Okay, for today, let me stop in here. Do you have any question?